So welcome back to Part 5 of Static and Current Electricity, Magnetism and Transformers, and we're going to focus on direct and alternating currents and plugs and sockets. Direct and alternating currents. So direct current, abbreviated as DC, is produced via cells and batteries. It travels in one direction from positive to negative and has a fixed size. Alternating currents are produced via a generator. It reverses its direction rapidly many times each second and its size varies. So here we have graphical representation of a direct current, alternating current and variable DC current. Okay, so direct current, there is no sine wave. There is a sine wave for alternating current, and when it comes to DC current, so basically what is happening here is that we have had alternating current that was rectified, and we're going to get into that just now. Now remember, when we were in waves, sound and light, we learned about frequency. So frequency is equal to 1 divided by the time it takes for a complete oscillation, or 1 divided by time, right? Frequency is measured in hertz, abbreviated as Hz, or 1 over S, which is the same as per second, S to the negative 1. Cathode ray oscilloscopes are expensive and can be difficult to operate. Most waveform analysis is now carried out using digital oscilloscopes, which can be connected directly to a computer. Plugs and sockets. We've seen plugs, we've seen sockets, and we know not to stick any part of our bodies into them, and we know we're not supposed to stick metal into them. You stick this into a socket and you're holding it, nobody could save you. I can't come and hold you, then current will pass through me, right? You may take a big stick, a big wooden stick, to remove you from that current. So please do not play with sockets. Do not stick anything into them. Be careful. The only thing you stick into a socket is a plug. Alright, so mains electricity in the Caribbean. Mains electricity is supplied as alternating current. Mains supply is usually noisy due to interference from other electrical devices. So here we have some examples. We have the island. In Barbados, the voltage is 115. The hertz is 50 cycles per second. And in Cuba, you have a voltage of 110, 60 cycles per second. Jamaica, 110 out to 20, 50. And if you look at it, you know, when you receive plugs from places like England or foreign countries, you realize it's different. So each country or territory has different voltages being transported to the homes. St. Kitts, where I live, is 110 or 230, and the hertz is 60 cycles. St. Martin, 120 or 230, 50 cycles, and then Trinidad and Tobago, 115, 50 cycles. So the mains supply voltage and frequency varies from island to island in the Caribbean, as illustrated above, for just historical reasons. Now, ring mains. An electrical configuration called a ring main is used as a basis for the connection of domestic power sockets. 2 or 3 wires are used in the ring main, and they are thick enough to provide a current to several devices at once without overheating. Remember, the fatter the wire, the less resistance and the less likely for it to overheat, right? Types of wire. So these are the names of the wires that are present within the ring main, and you've seen them. Some of you have seen them. If you open up a plug that's not connected to current, you would have seen these colors, especially in the current, the modern day ones. So the color of the live wire is brown, and it provides power and operates at a very high voltage. That's the one you don't want to mess with. The neutral wire is blue. It completes the circuit, allowing the current to flow in a closed circuit. The earth wire is green and yellow, so it is green and yellow stripes. It grounds the circuit to avoid severe shocks or even electrocution. So we have here, what does each wire do? And I said what it does, this is just a picture showing you. As you can see the green and the yellow stripes. This is brown, which is live, and the neutral is blue. And then we have the picture here for you to see. And there's a fuse always in there, just in case too much current is flowing through this. This fuse will break on command. When it's too much current, it's gonna break. It's gonna break the circuit. It's gonna burn out and break that circuit. So earth wire is yellow and green and connected to the earth pin. So the pins have names as well. So you have to match the wires to the pins, and you will see them having labels like L and E and N. So L for live, N for neutral, and E for earth. So you will see them, you have to match them up, otherwise you're gonna cause problems, right? So the earth wire is yellow and green and connected to the earth pin. A 2-core cable does not have an earth pin, which is the simple plugs. The simple plugs with 2 pins, they don't have an earth pin, which is the longest pin in the plug. And I wish I had the wire there. Let me see. I think about okay. So this is an example. 2 pins, and I don't have the triple one. If I unplug it, everything will go haywire. But I think you've seen triple pins. Then the pins in a plug are made of brass. Live wire is brown and connected to the live pin. And you have a fuse. The case of the plug is made out of stiff plastic. You have a cable grip. You have other insulation. The cable is copper, but it's surrounded by an insulator such as rubber, which is flexible plastic. Neutral is blue and connected to the neutral pin. And earth wires are essential for appliances with metal cases. If the earth wire becomes loose and touches the metal case, a large current flows to earth, blowing the fuse and breaking the circuit. Why don't birds get electrocuted but humans do if they perch on electrical lines? And when I looked this up, it said that birds are essentially poor conductors of electricity. If you have better answer, please provide it. Okay? Alright, so plugs and sockets. In the Caribbean, there are 2 main types and sockets used, and these are referred to as type A and type B. Type A plugs have only 2 pins which connect to the live and neutral wires. Type B plugs have 3 pins. The additional pin is connected to the earth wire. A type A plug should not be inserted into a type B socket. What would happen if a 110 volt device is connected to a 220 volt device? Yes, things are going to go wrong. Well, not really, because I've done that. It shouldn't be done. But the other way around, I think they've made these devices in such a way, especially if you have a 220. What would happen if a 220 device is connected to a 110 volt device? It's designed in such a way that the 220 device really cannot connect, but what would happen is that too much current would go into that device and cause it to overheat, or it would smash it up. And what would happen if a 110 device is connected to 220 device? Pretty much the same thing. So 110 would actually, if it's connected to 20, it wouldn't provide enough energy or enough current to that device, whereas the opposite would happen. 220 would be too much voltage, too much flow of electricity into that device, causing it to become destroyed, right? So connecting a device designed to operate with a 50 Hz supply to a 60 Hz supply or the reverse is also likely to damage the device, as its electrical components will not function properly or correctly. Why shouldn't you change the plug on an electrical device from a type B to a type A? What advantages does a rings main provide? Well, you shouldn't do this because the device is not going to work properly, number one. And number two, for this one, what advantages does a ring main provide? It contains a fuse. So if too much current enters it, it would burn and break easily. So it would stop that. And also, it contains an earth wire. So if it's connected to something that's metal, made of metal, all the electrons will be shot into the earth, and the fuse again would blow. It would burn and disconnect the circuit, right? So you won't get zapped. So mains electricity is dangerous. It can kill you. Protective devices are used to reduce harm to you or the device being used. Here are some protective devices. There are fuses. Description: fuses prevent current overload in a device. It also prevents fires from starting. Its wire is so thin that it melts when too much current passes through it. It does its job but has to be replaced once it has been used. Circuit breakers prevent current overload in a device. It uses an electromagnet to break the circuit when the current is too large. It does its job faster than a fuse. It is more sensitive and does not have to be replaced. It only has to be reset. The earth wire. The wire provides a low resistance route for the current to pass to earth. Therefore, the current will not pass through the user. It's quite effective. It avoids shocks and electrocution if the live wire becomes loose and defective. And here are some pictures of fuses, circuit breakers. You would have seen this. So I think you've seen all of them. You might not have seen a fuse, but you would have definitely seen circuit breakers in your house. Look for the mains, and you would see there is some switches, right? Circuit breakers, they are there to protect the wiring in your house, right? If you get a chance, you can actually go to your local hardware store and purchase a socket that contains an earth wire, and in there you can investigate, you can look at the pads and all that. What if there were no earth wire? If the case is metal and is in contact with the live wire, a user can receive a fatal shock on touching it, right? A fuse alone would not help, since touching would simply recomplete the circuit. The user would then become the path of least resistance, and you would now become the earth wire. You are now the earth wire, human earth wire. Some devices automatically protect the users because they are made from insulating materials such as plastic. So we're going to revisit alternating and direct current. Alternating current is much easier to produce from the generators in power stations. Some devices, including computers, require current at very steady voltages to operate correctly. Rectification is the process of converting an alternating current to a direct current. Rectification relies on the properties of diodes. The most common function of a diode is to allow an electric current to pass in one direction, called the diode's forward direction, while blocking current in the opposite direction, which is called the reverse direction. So here we have an anode, and this is how you draw it. So the anode, this is a diode, sorry, and you have the anode, which is the positive area, and you have the cathode, which is the negative area. So where the strip is, just know the strip is closer to the negative end. Simple. And you could also, you see how the diode is drawn here? This represents the strip. So where the strip is closest to is the negative end. Types of diodes, they're all here. You have single diode, light emitting diodes, IR, LEDs, photodiodes, transient voltage suppression diodes, all of them Shockley diodes, tunnel diodes, gun diode. It's a lot. Half-wave rectification. The current provided by half-wave rectification is direct in the sense that it is only in one direction. Remember I mentioned that word? Alright, so this is like rectifying alternating current. Applying a diode to obtain direct current is insufficient since there are gaps in the flow of current. To help with this, a capacitor is used. That's why you saw them so close, right? So the capacitor fills in the gaps. A capacitor is a device which stores charge for a short period of time. Adding it onto the simple half-wave rectifier diode produces a smoother direct current. When the voltage is rising and there is a current in the load, some charge will be stored in the capacitor. When there is a low voltage causing a low current load, the capacitor is able to release charge from its place and provide a current. The capacitor provides continuity of current when a diode is being used, making their use together more efficient. In half-wave rectification, you can see that only half of the alternating current is actually producing a useful direct current. So you see it here. And so a more complicated circuit involving 4 diodes can be used to produce a positive potential difference even when the alternating supply is providing a negative voltage. This gives full wave rectification, which supplies a much steadier DC supply. So here we have them connected due to the presence of a capacitor. So smoothed full wave rectification. So this is basically the capacitor, the diodes, yeah. Alright, so here endeth the 5th part of static and current electricity, magnetism, and transformers. See you around for the 6th part, which is logic gates. And please note that logic gates was actually done already, so I'm going to put a link so you can go there to see the explanation. It's an old video, but it's very essential. It's nice. But I'm going to still teach you. See you around. Bye.